Hello, hello. Yo, yo. Yeah, it's time to do some integrals. So, yeah, this is a dumb idea I got from... I was listening to a Tom Rock's Maths video, and he was talking about, I can't remember what question he was asked, but he basically said that, like, when he was in college on, like, Saturday nights and things, he would get together with the boys, and they would basically have like a drunk integral contest. They would have bring a bunch of beer, and they would basically all drink and see who could do the most integrals, while they're all getting progressively drunker and drunker until they just couldn't do it anymore. So that sounded like a pretty fun idea to me. So that's what I'm going to attempt to do right now, and I'm currently preparing for actuary exams, and I need to work on my integral chops. It's been quite a while since I've just done, calculating integrals. I've done like real analysis towards the latter half of my math degree, but that's a bit more involved and quite a bit different than just calculating the integrals. So it's been a while since I've done this. And I'm not very good at them, as you'll soon find. In preparing for actuary exams, most of the integrals that I've been doing so far have not been super complicated. Some of them require integration by parts, but they're usually quite doable. I just need to get better at them. And yeah, I thought this would be a fun little challenge. I'm not drinking beer, I'm drinking shochu here, because shochu is pretty nice. But yeah, so you're about to see American education on display. This is going to be embarrassing. I'm really not great at integrals. But yeah, this sheet is a sheet of 100 integrals that I got from a YouTuber called Black Pen Red Pen. He makes really cool math videos. He did a video where he did 100 integrals, and that's what this sheet is from. I have the answer sheet as well, so I can check my answers as I'm going. And maybe refer to the answers if I get stuck. I'm sure I will. Because I don't want to spend, 30 minutes on one integral. And then I've got these sheets, I think from like Paul's Online Math Notes, that are just like, basic integrals and derivatives that you should know, that I have kind of escaped my memory at this point, because it's been a while since I've done good old-fashioned calculus in college. And here's a sheet of like trig identities and stuff, because these will come in handy a lot as well. Yeah, and then on the right side of the screen I've got my little whiteboard. You can't see my pen moving around, but I can write. Oh shit, yep, there we go. Yeah, I can write on here. So, I guess without further ado, let's get started. And I've got some nice hoppin' music in the background that hopefully is at a nice volume. These first like 5 problems or so I've kind of already looked at and done a couple of them, because I did like a little test recording yesterday to test out the setup and all that. We should be good to go though. So first one, I'm not going to drink quite yet. I'll probably do a couple and then take my first shochu shot. So let's go. Q1. We've got the integral of tan to the 5th secant to the 3rd dx. I think what I want to do first is look at the derivative of secant. Yeah, derivative of secant is secant tangent. So I think that's going to be useful here. Yeah, I think we want to factor out one of what do I want to do? Yeah, I think I want to pull out one of the tangents. So, whoops, that becomes to the 4th. And then we'll pull out one of the secants as well, just for the heck of it. And then we'll end up with secant, tangent, dx. So now we have a situation, you know, we have a function and its derivative right here, so that would be a nice u-sub situation, but we still have the tangent to the 4th. I want to see if there's any trig identities I can use to change those tangents into secants. Yeah, so that's something we can do. I can, off on the side here, let me write it really small. Tangent to the 4th. This music is going to be a little distracting. Tangent to the 4th is tangent squared. And then each of those tangent squareds becomes secant squared minus 1. So that's secant squared minus 1 all squared is what we can turn that into. So I think we might be good to go. I think let's try that. Let's change those tangents. That becomes secant squared x minus 1 squared secant squared x secant x tangent x dx. Now we let u equals secant du equals secant tangent, and let's do our substitution. It's an indefinite integral, so thankfully we don't have to change limits or anything like that. So what have we got? That's going to be a u squared minus 1 all squared times u squared du. Now, do I want to just multiply this out? I think I'm going to. So I can just do the power rule and all that stuff. So, what would that turn into? Let me write that over here. That's just easier for me to keep track of things when I expand it out like that. So that becomes u to the 4th minus u squared minus 2u squared plus 1. And that's all multiplied by u squared. I really hope this turns out to be right, and I am not, you know, going down the wrong path this whole time. So now we gotta multiply in that other u squared. That's gonna be u to the 6th minus 2u to the 4th. I think you add the powers when you do that, yeah. Plus a u squared. Okay, should be able to integrate this now. Really running out of room. But we've got a 1/7 u to the 7 minus 2 over 5 u to the 5 plus 1/3 u to the 3. Now we have to back substitute. I'm not sure if I can make more room somehow. Yeah, let me just zoom out. Zoom out, lasso all this, and move it somewhere else. Okay. Okay, now we have to substitute our U back in, so 1/7 secant 7th minus 2/5 secant to the 5th plus 1/3 secant to the 3rd plus C. I know you can't see the plus C, but I did write it. Is that the answer? Hell yes, we are right. We did it. Booyah. Okay, yeah, that first one, that was already a doozy. But, let's lasso everything up here. That's 1 integral down out of 100. Zoom back into 100 here. Integral number 2. We've got cosine of 2x over sine x plus cosine x dx. So this screams a double angle formula. Let's go look at what that is. That's wrong cheat sheet. Okay, that gives us cosine squared minus sine squared. Not immediately useful, because we would like to cancel out that sine and cosine on the bottom. However, when you have the difference of two squares, like this, we can factor this as cosine x plus sine x times cosine x minus sine x. Yeah, so this numerator equals this. That's one of the double angle formulas, as you can see on the left. We can factor it as this, and then once we factored it like this, that denominator disappears. It cancels out with that one. So what we're left with is just a nice cosine x minus sine x dx. And that should be pretty easy to integrate. That's sine x. Second one, sine becomes minus cosine, but it's already minus, so it becomes a positive cosine. Plus c. Is that it? Answer sheet. Yep. We're still good. I still know what I'm doing. With that, I think we'll take the first shochu shot. After I won't get rid of this one yet. Alright, here goes. Yeah, and then I don't have the counter up there set up for me to like just press a hotkey and then it, you know, goes +1. I have to actually manually change it. So okay, cheers for calculus, I guess. Tasty. It's a little less tasty than sake because it's a little stronger. That's what we want. Itadakimasu. Okay. Question 3. This was one of the ones I did yesterday. This one is quite a handful. So I should probably write kind of small. X to the 4 minus x squared plus 1 dx. So that bottom isn't factorable as much as you would like to. It would be really nice if it factored to, you know, have a x squared plus 1 as one of its factors. That would be really nice. It doesn't work out that way. The hell? I'm hearing like a beeping or something. I think it's coming from outside. Let me make sure it's not my phone. Nope. Or I'm just going crazy. But yeah, so the solution of this, as hairy as it looks, is to factor an x squared out of both the numerator and the denominator. So that works out to 1 plus 1 over x squared, and then the bottom becomes x squared minus 1 plus 1 over x squared. And then I think this bottom at this point can be like rewritten in a certain way. I'm pretty much just remembering the solution from memory because I absolutely could not figure this one out last night. Like, I think this ends up being one of its factors, x minus 1 over x. Like, if you square this, I think it gets you something similar to this. So let me try that. X squared minus 1, another minus 1, and then no wait, how would that? X squared, x times 1 over x is 1, but it's a minus. Then there's, yeah, so it is minus 2. And then the last one is, it's a positive 1 over x squared. Okay, so this is almost the same as that, except that has a minus 1. So what we have to do is add a 1 to this. And then we can substitute this. But I'm now trying to piece together, like, what the point of doing that is. Wait, I think I remember. So, yeah, so let me just... I'm losing it already. This is still 1 over x squared on top. On the bottom is now this with a plus 1. This is equal to that. It just looks a little different. Now I think, excuse me, if we set u equal to, excuse me again, that factor right there, x minus 1 over x, the derivative of that becomes 1. This is a minus x to the minus 1 power, so if we bring the power to the front and then subtract 1 from the power, that should give us a positive 1 over x squared. Yes. Also, those are supposed to have dx's. So yeah, this is the whole point of going through this rigmarole, because we now have a function x minus 1 over x in the denominator, and then its derivative is in the numerator, so we can pull off a u sub. So we've got in doing that, we'll have a 1 on the top, du over here because I just like to put it on the side. And then this is this. It's u squared plus 1. Yeah. And now we can finally, now this finally looks like something that we can integrate. It still looks a little tricky to integrate, but I think this is a trig function, is what the derivative of, yes, it's inverse tangent. Derivative of inverse tangent has this form, 1 over x squared plus something. So that's what we got. That means this is going to be tangent inverse of u plus c. Now we just gotta substitute in what u was. U was 1 minus x minus 1 over x plus c. Is that the answer? Yes, that is the answer. Yeah, that's a hairy one. That is one that I guarantee you I would not have figured that one out on my own. So let's lasso everything out of here. Almost everything, because I'm sloppy. Okay. Number 4. We've got the integral of x plus e to the x to the square dx. Yeah, the way I do this one is just multiply it out. So let's be careful about this and actually write it out, because it's easier for my brain. So that works out to x squared plus x e to the x plus, so that's 2x e to the x's. E to the x times e to the x is e to the 2x. Okay. And now we can just integrate each one of these individually. This is one of the ones I did yesterday. I can't think of a way to u-sub this and sort of do it in a nice sleight of hand. It really looks like there should be some kind of u-sub you can do for this, but I can't think of one. And it's easy enough to just integrate these individually. So the first piece is obviously just 1/3 x to the cube. This one is going to be 2 times something. This one we need integration by parts for. So let's do the DI method on that. That's x and e to the x, that's 1 and e to the x, that's 0 and e to the x. And then we multiply them like this. So that's going to be 2x e to the x minus 2e to the x. And then this last one is going to be 1/2 e to the 2x plus c. That should be our answer for this one. Yes, looks like we got it. Yeah, I did that one yesterday, so no big deal. I should be able to do that one. Let's erase everything with the eraser. It's more work, but whatever. Oh wait, I forgot to update the shochu counter. Oh my god. That's gonna be an ongoing problem, I bet. Okay. Okay. Integral number 5. This one is going to be brand new material for me. I haven't looked at this one or attempted it yet, so what have we got? We've got cosecant to the third times a secant. Huh. Well, let's look at our trig identities. See if there's anything we can do about this. I know cosecant is 1 over sine, secant is 1 over cosine. That might be something, because then we would have a function and its derivative, right? So we might be able, that might be the way to go. Might just be able to do a u sub there. Yeah, let's try that. We have 1 over sine to the cube times 1 over cosine. Should I write it like that? Let's see if I can do this. I don't know if this is allowed, because surely we can do this, right? Surely we should be allowed to do that, and then, you know, let u equal sine, du equal cosine, and then we've got 1 over u to the third du. Oh no, the du specifically would be in the denominator. Huh. Yeah, I don't know. Let me see if there are any identities that would be useful specific to cosecant and secant. I'm not really seeing anything. Oh, we have cosecant squared equals 1 plus cotangent squared. Would that lead to anything useful? I don't know. It's possible. Let's just try that root on the side. So if we sort of factor out one of the cosecants, then we're left with cosecant squared here. We know that cosecant squared is equal to 1 plus cotangent squared. This cosecant is equal to 1 over sine. This is 1 plus cotangent squared, but cotangent is equal to cosine over sine. So cotangent squared would be cosine squared over sine squared. I wrote that wrong, but whatever. Let me fix that real quick. Okay. If we multiply in the sine, we have this plus cosecant, or cosine over sine cubed. And then we would have this chunk multiplied by a secant x, and secant is 1 over cosine. So we'd have 1 over cosine sine plus cosine over sine cubed x. Does that make things any easier? This could be differentiated with a simple u sub, because it would just be 1 over u cubed du. So we could do that. It's just this piece. I feel like there's some kind of something that we could do with that. Okay, so I can integrate some of this. I'm just drawing a blank on what to do with this here. There's the double angle formula that's 2 times this, but like... you know, so I could replace this with a 1/2 sine of 2x, but then I don't know if that'll be any easier to integrate, you know? I don't know. Let's just write it that way. So this piece we know is just 1 over u cubed du, plus the other piece is 1 over 1/2 is 2, so we could pull the 2 out to the front actually, and then this just becomes sine of 2x dx. What do we do with that? That gets us to cosecant of 2x. We could just do the integral of cosecant. Is that oh man, I didn't mean to close that. Damn it. Okay, but yeah, is that a common integral that's on this sheet somewhere? Trig functions. Cosecant is ln of absolute value cosecant minus cotangent. Oh, there's also one for cosecant cubed. Huh. Interesting. Yeah, so I guess we could just do that. So let's integrate this. This is u to the -3. So we're going to add 1 to the power, divide by the new power. That's going to be a minus 1 over 2u squared. Yeah, that sounds right. And then this is going to be, we're thinking of this as cosecant of 2x, because that's what it is. So that's going to be a 2, the derivative of cosecant or actually we divide by the derivative of this 2x on the inside, so that actually cancels out the 2. And then we just get ln cosecant of 2x. I need to erase this junk on the side. I'm going to be angry if this turns out to be wrong. It's probably going to be wrong. Minus cotangent of 2x, absolute value, plus c. Right, we need to... u was just sine, so... let's change that to sine squared x. Okay, please tell me this is the right answer. It's not looking right. They've got ln tangent minus half. They've got ln tangent minus 1/2 cosecant squared x. Okay, well the 1/2 cosecant squared x is equal to this. So this part's right. ln of tangent, though, where did that come from? Is there a trig identity with tangent and cosecant and cotangent? Probably not. Yeah, I don't think so. So let's see where we went wrong. That's lame. Super lame. Alright, so how did they do it? They did... This was kind of my original idea. And then, what did they do? I guess they replaced the 1 with a sine squared plus cosine squared. That cancels out some stuff, and then you end up with this, which is still equal to 1. And you have cosine over here. And then what did they do? But yeah, okay, so they broke this up, so they canceled the sine out of there, cancel the cosine over here, and then they just have sine over cosine plus cosine over sine plus this piece at the end. Right. So sine over cosine is just tangent, I think. This is just cotangent. And what are the derivatives of those? Or the integrals of those? Yeah, cotangent is just ln sine. I want to believe that my answer is right somehow, but yeah, I really don't think it is. Using the double angle formula was not the right way to go. But yeah, right, this is cotangent, that's tangent, and then this was the one piece that I did right, because I did it by u sub, and they got the same answer for that. But yeah, is there any possible way maybe that we can think of this as being equal to this? I don't think so. Oh well, we'll chalk that one up as an L. I was sort of close. Yeah, that one was kind of tricky. I had an idea of what to do, though. I feel like there's a number of routes you could have gone with that one. Oh, more trig stuff for number 6. And I think I'll have another shot of shochu while I'm at it. Should I take a shot for every wrong answer? I'm taking shots regardless of what I get for answers. That's the whole point of this. So, you see, if we take the shochu counter and we add 1 to it, we get 2. And that's really interesting stuff. Okay, so this one looks really fun. Integral of cosine over sine squared minus 5 sine minus 6. Why is there a quadratic? Okay, are there factors of minus 6 that add up to minus 5? Yes, there are. Minus 6 and plus 1. So let's deal with that first. That's gonna work out to be sine x plus 1 over sine x minus 5, right? You get sine squared minus 5 sine. Oh no, 6, not 5. Minus 6 sine plus 1 sine, and then the minus 6, right. Okay. Question is, what good does that do us? Oh, well, we have a function and its derivative. That's what it does for us. So that just becomes 1 over. Actually, yeah, we didn't even need to do that, actually. We could have just called sine to be u, du is cosine, and then, yeah. So this is just u squared minus 5u. Minus 6. Question is, we still have to integrate that, which is not really fun to integrate. Let me write it this way. U plus 1, u minus 6. And then let me think of this as u plus 1 to the minus 1 times u minus 6 to the minus 1. Can we integrate that? Surely we can. Or actually, no, it would be easier if we just raised all of these things to the minus 1 power, I think. But, I still really don't like this. I feel like this should be so easy, and I'm just missing it. I think this deserves a minus 1 to the intelligence counter. This is just a simple polynomial, but it's in the denominator. That's what I don't like about it. Oh my god. Would I, like, partial fractions this, maybe? The thing is, I'm not really well practiced when it comes to partial fractions. I had to kind of refresh my memory on how to do that the other day. I think this little cheat sheet talks about it. So this is the case where we have irreducible linear factors. Like, so does that mean it would be equal to like a over u plus 1 plus b over u minus 6, and then we have to figure out what a and b are? I forget how exactly to do that, though. Find the partial fraction decomposition of the rational expression, integrate the partial... Right, yeah, so I think I've got this right. I just forget how to, like, solve for a and b. If we can solve for a and b, then I know we can integrate this. I don't want to, like, have to, you know, stop this and go look it up, but... Like, there's the cover-up method, but I forget how exactly it works. Like, if I want to solve for a, which one do I cover up? Is it u plus 1? Oh god, I'm so confused. Okay, I'm gonna look it up real quick. Or, you know what? Yeah, I'm just gonna look at the answer. I was on my way to it. So what did they do? They got to this point. Yeah, so yeah, they did partial fractions. U minus 6 equals 0 when u equals 6, right? Sub u equals 6 into u plus 1, that equals 7. So that means a is 1 over... No, my a, in my case, would be minus 1 over 7. Sub u equal minus 1 into u minus 6. That gives you minus 7. Yeah, so I understand the solution. I'm not well versed enough in partial fractions to know how to do it, and it's a shame too because that was a really simple partial fractions example. But yeah, so for me to solve for a, I would have to sub minus 1 into this expression here. And then minus 1 minus 6 is minus 7. But that's what I don't get. If I were to sub a minus 1 into this, wouldn't that just zero the denominator? And that's... We obviously don't want to do that. Oh, no, wait. I think I get what's going on here. You have to imagine that you're, like, multiplying... When you're solving for a, you have to multiply everything by this. Those two cancel. This denominator cancels. And then you have the u plus 1 here still. And then what you would end up with is 1 over... 1 over minus 7 because you plugged a minus 1 into that. That equals a plus minus, that's the, yeah, this zeroes out, so that term goes away. Right, okay. I get it now. So if I run into another one like this, I know how to solve it. Jeez. I think the shochu is getting to me a little too much already. But yeah, that makes sense. So that's how we get A. B is going to be a positive 1 over 7. And so this... yeah, this integral works out to be minus 1 over 7 over u plus 1 plus the integral of 1 over 7 over u minus 6 du, du, and that's minus 1 over 7 ln of this. Right, and then the derivative of it is just 1, so the reverse chain rule is not really a factor there. U we substituted to be sine in the first place, so that's going to be ln, probably want absolute value bars, sine x plus 1 plus 1/7 ln sine x minus 6 plus c. Was that the answer? Yeah, that is the answer. They just wrote it differently. They used the log property where the difference of, like, if you have ln of a minus ln of b, then it's equal to ln a over ln b. That's the property they used. Makes the answer look a little bit neater, I guess. That is the same as this, though. That was a little ridiculous, but yeah. I know how to do partial fractions now, so... where's the... There we go. I was looking for the trash can. I wanted to throw it all away. Okay, that was number 6. Number 7. We're finally scrolling down a bit. Oh boy, now we've got some stuff involving E. It's been about an hour so far. It doesn't feel like it's been an hour. It just... yeah, I'm very slow at solving math problems, so it just kind of goes slowly. So 1 over the square root of e to the x. Huh. Well, we can think of this as e to the x to the minus a half power. The question is, does that help? Because I can integrate e to the x, I just don't know if I can integrate that raised to some power. Oh wait, yeah, if I... duh. This is just e to the minus a half x dx, and then I just integrate this the way I normally would. But divide by the derivative of this. If I divide by minus a half, that's like multiplying by minus 2. Is that the answer? Yeah, that's the answer. They just decided to write it a little bit neater. Okay, I got one right. And I did it rather quickly. Not bad. My brain is still working well enough to do these kinds of problems. That one wasn't too hard though, thankfully. The next one though, question 8. Oh my god, what is this, dude? E to the x, square root of e to the x minus 1, e to the x plus 3 dx. This is stressing me out just looking at it. How the hell do you do this one? U-sub, maybe? Also, what's up, Duck Ixiel? Welcome. Yeah, I'm just... let's see, what would you set U equal to? Maybe the square root thing? The bottom, probably. Okay, then we would have 1 over u, and then... Yeah, and then if we subtracted 4 from this, that would give us that inside. Right, that's u minus 4 would give us e to the x minus 1. This is just u, and then that's du. Yeah, that looks a lot simpler. Now this should be easy to do, but I don't know, would you have to, like, do this by integration by parts? Like, could I think of this as a product of the numerator times the denominator, basically? I don't know if that would just overcomplicate things. You have no idea. Yeah, neither do I. I mean, I'm almost certain, like, this is the way to go, because that looks a lot simpler than what we started with. Like, that seems like that should be doable. And, like, integration by parts can't be wrong. It just might be a lot of work. I don't even know... Maybe we can call this 1 over u. I don't really want to integrate that, though. What's the derivative of... No, the derivative of 1 over u would just be the power rule. I can never remember, because I think the derivative of ln x is 1 over x, and then it's the integral of 1 over x is ln x. Yeah, that would be ln u. Or, wait, what? Yeah. No, I had it backwards, you're right. I've got a cheat sheet of, like, table of derivatives and stuff here. Nope, I think that's wrong. It's the derivative of ln is... derivative of ln x is 1 over x. So, I mean, if I put this in the integral column, I could integrate that to ln u, but then I would have to differentiate this, which I don't want to do. Well, that's just u minus 4 to the 1/2 power. Maybe substitute root u minus 4 as s. Let's try that. Yeah, when I was in school, I don't think I ever did like a nested substitution, but that could work. Okay, the derivative of this, why is this so hard for me to figure out? Do I have the derivative of like the square root of something in this table? Chain rule, you think? Oh yeah, I think you're right. Yeah, it would just be 1 over 2 root u minus 4. But the derivative of the inside is just 1. Yeah, it's just a power rule. Yeah, you're absolutely right. Yeah, that doesn't exactly help us, though. I'm very tempted to just look at the answer at this point. Let's see. What's the next one? God, the next one looks bad, too. Yeah, I don't think the S substitution really gets us anywhere. And then integration by parts I don't think would get us anywhere, because differentiating the numerator, like, I don't see where there would be a stopping point for that. Although, I forget what the stopping points are for the DI method, though. I think it's when you have a row that you can integrate. Something like that. So let me do that again, since I now know how to differentiate that. So u minus 4, we know that this is 1 over 2 u minus 4. 1 over u is ln u. That's not any easier to integrate. And I don't think it's... I think it's just going to get more complicated the more we continue with this. Let's try the other way. So if we differentiate 1 over u, that's u to the minus 1. That becomes minus 1 over u squared. And then this piece, how do we integrate this? I wrote that really poorly. Well, you can think of this as the power rule. That would be to the 3/2 divided by 3/2, so it would be like 2/3 u minus 4. Something like that, I think would be the integral of that. So can we integrate this row? I guess we can. Okay, so this would be like our u, this would be dv, so it's uv minus the integral v du. If we write that out, we've got 1 over u. We're using u twice here, but that's okay. V is this mess. Minus integral of v du. That looks horrible. Yeah, I don't want to integrate that. Let's see what the answer is. Okay. What did they do here? Seriously, what the heck? Is there a side note? Let u equal this. Du equals that. Dx equals this. Huh. So I guess the path to victory was to u sub this instead of the denominator. I really thought the denominator was a good idea. But yeah, then you end up with this. God, what do you do with this? Yeah, that one's pretty heinous. Let's move on to number 9. Number 9 doesn't look very friendly either. I just don't like square roots, man. 1 over x plus square root of x. So what the hell do we do with this? Let's try setting you to be this. That's one thing I want to clarify a bit. When they let du equal this, dx, and then dx was just the reciprocal of that. Yeah, I guess you would just multiply both sides by the reciprocal of this. Yeah, this isn't really all that useful. I wonder... No, partial fractions you wouldn't do here, because that's not a product in the bottom. I really want to break up that denominator, but we can't. God, what the heck do you do for this one? There's got to be something I can do at the square root of x. But I've just got no ideas. This one's even more basic than the previous one, so I feel like it's even harder, because there's nothing to manipulate. Yeah, I'm super stumped. Maybe set u to be the whole denominator? What would that get us? That would still be... That would just be... Yeah, that would just be this. Which doesn't appear to do us much good. I wonder... What if I factored a square root of x from the denominator? That would be... this, times square root of x plus 1. Would that get us anywhere? That might get us somewhere, because we would have... Oh, whoops, I'm writing behind Satonia here. Let me just write this. Yeah, because the derivative of this piece is just this, but with another 2. It's multiplied by a 2. So... okay. So if we multiplied by 2, 2 du equals 1 over that dx. That might be getting us somewhere then. Yeah, so if we set u equal to this, that's just 1 over u du, but with a 2 in front, I think. It doesn't feel legal to put that 2 there, but it might work out. So yeah, integral of 1 over u, I think, is ln. I always forget. Yes, it's ln. So we get 2 ln u. U, we said, was this whole mess, so that's 2 ln... yeah, we don't need absolute value bars because this is always positive. Plus c. Is that it? Yes! We figured it out! Oh my gosh. I figured it out. Yeah, so what did they do? Yeah, obviously we can't do that. So they let u equal root x plus 1. Yeah, that was the key to factor out that square root of x in the denominator. That actually ended up being fruitful. Very nice. I think that deserves another shot. I can't believe I actually did that one. It may have taken me like 10-15 minutes, but I figured it out. Let's see, what's the next one? The next one looks like a simple one, but it involves absolute value, which I can never remember how you're supposed to handle that when it comes to indefinite integrals, or definite integrals. I can't believe it. We did it. That was a nice moment. Okay, question 10. Yeah, so this is our first definite integral. X minus 3 absolute value. Okay, so I'm pretty sure the way to do this is you break this up into 2, where it goes from minus 1 to 0 of something, and then it goes from 0 to 5 of something. Well, let's see, what happens when x it goes from 0 to 5. If x is 0, then it's minus 3, which the absolute value bars would make it positive 3. Yeah, I really don't... I've always been confused about how to handle these. Maybe I just have to go from 3 to 5? Three, 5, and then this would just be x minus 3. I can drop the absolute value, but what do I do about this one? Would this go to from -1 to 3 then? But then what do I write? What am I integrating? Because anything, yeah, anything less than 3 and that expression in the absolute value bars turns out to be negative. Absolute value of a negative is positive. So I don't know. Maybe I plug in the limits, like -1 into x, -3, that would be -4. I don't know. I just really have no idea how to handle this. It's simple, but I just don't know how to handle absolute value when it comes to this. What the heck? Okay. So they decided to graph this. The graph of the function. Oh, it's not x minus 3, it's x plus 3. What the hell? That's stupid. The thing I don't understand is why they did y equals absolute value of x plus 3 instead of x minus 3. I don't get that. I guess it doesn't really matter in this case because the areas that you're adding up are going to be the same. It's going to be this triangle plus that triangle, but that's kind of lame. There's definitely an easier way to do that doesn't involve doing areas of triangles. I mean, not that this is super hard, but like, I don't know. That's something that I gotta look up later, how to handle like absolute values with these kinds of integrals. Because there's definitely a sleight of hand way to do it. Where you, I've done some of these before where you just break it up into 2 integrals, but you change the limits. Yeah. Lame. The next one. The next one I'm kind of dreading. Number 11. So, this is what we have for number 11. I don't know, let's look at our trig identities for a secant. They're not down there. Yeah, I believe a secant squared is secant squared equals tangent squared plus 1. That's fun. Well, what's 1 over secant anyway? What does that work out? Oh, that's just cosine. So this is basically just... Oh, okay. Well, that becomes a lot easier. This is just sine x cosine to the 2019 dx. U equals sine, du equal... Oh, huh? Yeah, du is cosine, but there's 2019 of them. Any other trig identities that we can make use of here? Integration by parts? Yeah, I've been defeated. I thought I figured it out. Yeah, I could raise both sides of this to the 2019 power, but I don't think I can really do that with the dx there. This is a bit messed up. Maybe it's worth it to leave it in secant form. I don't know. Maybe there's some trig identity that will just make this a piece of cake, but I'm just not seeing it. But yeah, we have a cosine squared equals this mess, but I don't think that would really simplify things. So I don't really want to use that one. Secant squared equals tangent squared plus 1. I don't think that would make things any easier. I mean, what I want to do is just let u equal cosine, and then du is minus sine dx. if we divide both sides by a -1, we get a minus du equals sine x. Maybe that's it. Maybe we just pull the minus out front. Yeah, I think that's the solution. It's just this minus sign. I feel like it changes the original. But maybe not. I think it might work out to be a legal move. So yeah, we have u to the 2019 du, and then the minus out front. So that's 1 over 2020 u to the 2020 negative. And then u is cosine, so we have minus 1 over 2020 cosine to the 2020 x plus c. Is that the answer? Yes, that was the answer. Yeah, that was a really easy one. I just I don't know. Usually, you know, the integrals that I do out of textbooks and stuff, I'm not used to having to go beyond. Usually, you just decide u is going to be something, and then it's like you figure out what du is, and then you do your substitution and you solve the problem. I'm not used to having to go beyond that, but it is sometimes useful to go beyond that in cases like this. So that was one that we figured out. That turned out to be an easy one. Oh, the trash can is up here. There we go. I can just hit the delete key. I gotta remember to do that. Set this back to 100%. Also, I think I'm gonna take my first bathroom break of the stream. So, BRB, enjoy the music while I'm gone. Oh yeah, also, because I've got a whiteboard right here, I can just go. All right, be right back. Okay, we're back, and we've got a bot in the chat. So, oh god, I don't know what to do. I can't do anything from the chat window in OBS. Hold on. Let me take care of that. See if I can. Why is it so hard to just, like, delete a message from chat? I'm literally the one broadcasting. Why... Why do they make this so difficult? The only options I have are to, Okay, I just banned them. I guess that's what I have to do. Okay. Also, I think it's time for another shochu shot. Because clearly I'm not impaired enough yet. Delicious. All right. Back to the integrals. So, what have we got this time? We've got x to the inverse, x times inverse sine of x over square root 1 minus x squared. What is the derivative of inverse sine? That's what's shouting out to me. Yep, there we go. Boom, we've got a function and its derivative. We've also got an x there, though. That's a bit pesky. But, yeah, what I really want to do is this. Thing is, we need to take care of that x somehow. Could multiply both sides by an x, but, well, we could maybe solve for x to, figure out what it is in terms of u, since we have u equals inverse sine of x. How would we do that? Do we just take the sine of both sides? Is it like sine of u equals x? Surely that's it. So, let's try it. X is sine of u. Inverse sine is just u. And yeah, we don't even need to write it like that. U sine u du. This whole bottom part and the dx is du. So now we can just product or integration by parts this. Di u 1 0, and we've got sine minus cosine of u minus that's going to be minus sine. So multiply that by that by that. And the answer in terms of u is minus u cosine u plus sine u. Plus, we don't need the plus c yet. I gotta back substitute for u. So u is inverse sine of x, cosine of inverse sine of x. This is a bit messy, and then sine u just equals x. So is that the answer? Apparently not. It looks very similar to what I have. Yeah, the only thing different in the answer is the cosine of the inverse sine. Yeah, how did they work that out? So they said, It's weird that they just went straight to integration by parts on this. Yeah, maybe I can't do it the way that I originally did it. Because my answer is so close to what they came up with, I feel like I can't be completely wrong. I'm trying to figure out if I, like, missubstituted things. Like, what does cosine of inverse sine of x work out to be? I don't know, if you do some trig, it probably works out to be this. So, I don't know. I stand by my answer. I think my answer is valid. I don't know, is there any easy way that we can easily write cosine in terms of sine to simplify this? Not really. This music is so hoppin'. I had to choose a nice, lively, bumpin' music for this stream, because I certainly can't liven things up. Yeah, I'm going to accept my answer as correct. Even though it is unconfirmed. unconfirmed, but I believe in my answer. I'm not going to pull the 2. I want to pull the 2 out, but just in case that isn't worth doing, this is one where we definitely want to look at our trig identities. So sine of 2x is 2 sines, 2 sine cosine. That might be the way to go right off the bat, because the 2 sine cancels with the numerator, leaving us with 1 over cosine, and 1 over cosine is 1 over secant. It's secant. And the integral of secant is, I think, ln of absolute value tangent plus secant, or something weird like that. You can't expect me to memorize this stuff, come on. That's the derivative. Where's the integral? Integral of secant. Integral of secant. Yep, it's ln secant plus tangent. So that's the answer to this. Ln secant plus tangent plus c. Is that the answer? Heck yes. Why did they do it this way? I guess they just did it like assuming you don't have access to those like table of integrals, those like common integrals. Yeah, because I guess then you could just let u equal that, du equals that. That's a clever way to do that. So I guess that's where that common integral comes from. That's neat. I'm not good enough to do that. I just use the table. Okay, next one. Been doing a lot of trig. Question 14. We've got cosine squared of 2x. So immediately what I want to do is expand this out as cosine 2x, cosine 2x. And then see if the double angle formula can lead to anything fruitful on that. Let's see. Cosine squared x minus sine squared x, cosine squared x minus sine squared x. I wrote that wrong. dx. So now we have a function and its derivative, sort of. Yeah, no, we definitely don't. I don't think we can just swoop in with a u sub here. Well, the Pythagorean identity says sine squared x plus cosine squared x equals 1. So is there any way that we can get this to sort of look like this arrangement? I don't know. I could just do integration by parts at this stage. I don't know if it would lead to anything fruitful though. I could try it. I might... Yeah, I actually don't know if I would end up with anything useful, because no matter what I do, I'll always end up with both cosines or both sines in each row. Oh wait, I can change... Will this help? I can change just one of these to a 1 minus 2 sine squared. One minus 2 sine squared x dx. This is tricky. But it shouldn't be. I feel like this should be easy. There's just something here I'm not seeing. Man, this is some serious dead air. I'm also starting to get pretty drunk now. Oh God, what the heck can I do here? Well, I can go back to the drawing board a little bit. Let me use this trig identity. That would equal 1/2 times 1 plus cosine of what was on the inside, which is now 4x. Yeah, that makes sense. So can I integrate this? Well, we've got 1/2 plus 1/2 cosine 4x. Yeah, that should be doable. Yeah, I think that's the way to do it. So this gives us 1/2 x. This gives us 1/2 times, this is going to be a sine of 4x divided by the derivative of 4x, which is 4. So it's going to be a 1/8 sine of 4x plus c. Let's pray. Let's pray. Please tell me I'm right. Yeah, baby. Took me too long to figure it out, but I figured it out. I figured it out. That's all that matters. Okay, question 15. We've got 1 over x cubed plus 1. Is the bottom factorable? I don't know off the top of my head. I kind of want to try a bunch of different ways of factoring it. Yeah, because it's an odd power, like I feel like x minus 1 might work out that way. So we have x squared minus 2x plus 1. X minus 1, that gives us x cubed minus 2x squared plus x, and then minus x squared plus 2x minus 1. That cancels with that. Yeah, that definitely doesn't work out to that. So it might be some other weird combination, like if I changed this to a plus, let's see what happens. X cubed minus 2x squared plus x squared minus 2x plus 1. No, that definitely, forget it. I don't think it factors. Is this another weird situation where we have to like factor an x out of the denominator? Or maybe factor an x squared. I don't know. I think I'm going to need another shot of shochu if I'm going to go down that route. So, let's pour one out. Kanpai, itadakimashu. Cheers. Ah, tasty. Okay. Can we do some kind of U sub here? Oh wait, I have to update the shochu counter. It's very important. I'm not seeing a U sub that would really help us here. We could factor an x squared out of the denominator. Maybe 1 over x squared. Let's try that. That would be minus a half, minus a half x to the third. Yeah, no, that bad idea. Just x squared, and then du would be 2x. But I don't think that does us any good. This is one of those problems that looks really simple but is actually really hard. That's integrals for you. I think this would be a lot easier to differentiate. Yeah, there's got to be just some magic sleight of hand to this problem that I'm not seeing. Very tempted to just go to the solution at this point. Yes, math indeed. Math is fun, I swear. Yeah, do you know what song this is? I don't know if you've played this game, the game that this is from. Yes. I love this song so much. I heard this song a lot from playing the like Connect 4 game, because I had to play that a ton of times to master it. It got pretty difficult when I tried to beat the impossible CPU. Yeah, it's a fun game. Yeah, I'm just gonna look at the solution on this one. I'm really out of ideas. Wow, this one gets quite complicated. Is there an aside? Oh, there is an aside, but there... Okay, so you're supposed to factor it this way, and then do partial fractions. Jeez. Yeah, I don't think I would have thought to do that. I just took one like 5 minutes ago, so not for a little while. I feel like I'm kind of reaching the limit. That is definitely not one that I could have done with how drunk I am at the moment. I will try to take it easy. Okay. Well, it's not the double angle formula, but what is it? The half angle formula. That's kind of jumping out at me, but I'm not sure if that would make this any easier. I could just do integration by parts on this, but the problem is I don't know how to integrate this or differentiate it. So I've got to do something to this. Which I guess the half angle formula would be what I need to do. So let's try that. We can pull the half out front, and that becomes 1 minus cosine of 2x dx. And then let's try I still don't want to integrate this by parts because I want to differentiate this because it's easy, but I don't want to integrate this. I guess I could integrate it. Yeah, it's actually not that hard now that I think about it. I'm reaching the limit. I don't know how much more integrals I can do. But yeah. So DI method, which I just learned a couple days ago, and I think it's really nice. I wish I learned it in school. So this becomes 1, that becomes 0. If we integrate this, that becomes x minus a half sine of 2x. And then integrate that one more time. Yeah, are you following this, Anthony? That becomes 1/2 x squared. Integral of this becomes integral of sine is minus cosine. It's minus cosine, so that becomes positive. But I have to divide by the derivative of what's inside, so that becomes a 4. Okay. So we've got 1/2 times x times this. This is going to be so messy. X times x minus 1/2 sine of 2x minus 1 times this. One half x squared plus 1/4 cosine of 2x. Okay, yeah, and then the 1/2 is multiplying this whole mess. So I guess we'll try to clean this up a bit. That becomes 1/2 No, let's work from the inside out. So that's x squared minus 1/2 x sine 2x. Excuse me. Minus all of this still. And then multiply everything by 1/2, we get 1/2 x squared minus 1/4 x sine 2x. There's no way this is going to be right. Plus c. Okay, is that the answer? Close. Oh wait, yeah, no, that is the answer, because 1/2 of x squared minus 1/4 x squared is 1/4 x squared. Yes, I did it. Oh my god. I can still integrate, I'm still in this. That was a good one. So what was that, 16? Oh boy, 17. God, I can't even erase anymore. Okay. 17. I really don't like the look of 17 already. I guess we could start by multiplying this out. That becomes x squared plus 2 plus 1 over x squared. Oh, yeah, we can just do the power rule on all that. 1/3 x cubed plus 2x plus, this is x to the minus 2, so we gotta add 1 to the power and divide by the new power. So is that it? Hey, yeah, that was an easy one. Nice. Okay. I think it's time for another shochu shot. I think I've earned it after those two. Yeah, cheers. Okay, number 18. We've got 3 over some kind of quadratic. Kanpai! Itadakimasu! I need to drink some water too. Okay, so 29 has no factors, so that denominator is not factorable. So this looks kind of heinous already. This looks really heinous. God, what the heck do you do with this? Use of the denominator, maybe? Or some portion of the denominator? I can pull the 3 out front. That makes me feel better. Yeah, I'm not seeing anything I can do with this one. I really wish the denominator was factorable. Thank you for believing. I'm not sure if I believe. I might have to look at the solution for this one. Oh yeah. Considering my current mental state, I prepared that image. I should have switched to that one a while ago. Let's see, if I factor an x out of the denominator, I get this. But is that going to be useful? Yeah, I've got no useful ideas on this one. We're cheating. Wait, what? Aside, this equals... Oh, I think they completed the square. Yeah, that's something that's worth trying with quadratic polynomials that don't look factorable. I just can never remember how to complete the square. Because in high school, ever since we were in the quadratic formula, that's just kind of what I always go to for solving quadratics. So I forgot how to complete the square. I don't remember what the formula is for that. But I think that's what they did here. Because this becomes factorable to x plus 2 squared plus 5 squared from the 25. And then once you have that, how did they go from that to this? I'm kind of struggling with that. Excuse me. Let me see, yeah, that's inverse tangent. Let me see what the derivative of inverse tangent is. That's 1 over 1 plus x squared. When the solution doesn't give you the answer. I know. Yeah, you have to decode the solution to get the answer. 1 over 1 plus x squared. So we have 1 over... I guess this is acting as a 1 plus x squared. So... I guess they're pretending that this is like a... I don't even know. I don't know if I can explain this. I sort of understand it. Yeah, that's pretty tricky. That's a clever solution, though. I would not have spotted that. I guess let's try the next one. Hold on. Can I just Control A? Oh, easy. Yeah, there we go. But then... Oh no, what happened to my tools? Oh, there we go. Okay. 19. Five cotangents. What can we do with that? Do I even have any trig identities involving cotangent? I'm sorry if I'm just blind, but I'm not seeing any. There's got to be something with cotangent. Oh yeah, here we go. Cosecant and cotangent. So that's equal to cotangent squared is cosecant squared minus 1. The other route we could go is look at this as 1 over a tangent to the 5th. Let's try this first. So cosecant, cotangent squared is cosecant minus 1. Does this help? Not obvious. Oh wait, cotangent is also just cosine over sine. So that's another route we could go. Let's try that. I don't know where to go from here. I want to do a U sub, but I don't think we can do that because there's 5 cosines. If there was just one, that would be really nice. I might be kind of out of ideas on this one. I don't know. I'm seeing some stuff that can maybe happen, because all the half-angle formulas, I feel like we might be able to get something out of them. God, this is getting so hard. Okay, let's... No, it's not to the 5th anymore. I'm gonna change 2 of these cosines to this half-angle formula. So 2 of them would be 1/4 and then this thing squared. One plus cosine 2x squared, I think. And then we can do... Oh no, that's 1 minus. We can do the same thing to the sine. But this factor here is cotangent. But yeah, I feel like we can take this other half-angle formula and sort of do a cotangent version of it. Whoops. Because if we take 1 over tangent squared, excuse me, I'm getting really gassy all of a sudden. But I gotta flip this whole thing. 1 over tangent squared. Wait a minute. God, I'm so confused at this point. I don't know if I can do this one. Okay, so what they did for the solution, they changed it into this. Excuse me. They changed it into this. And then they used the half-angle formula, like, sort of like I was doing. And then from there, they were able to do a U sub because they had a single cosine, right? I wish I could have thought of that. Yeah. Yeah, that's really all you needed to do, because cotangent, it being in terms of cotangent, that set you up to have it in terms of sine and cosine, and when you have sine and cosine, you probably want to do a U sub, so all you had to do was just get a single cosine somewhere, a single cosine in the numerator, and then convert everything else to sines, if possible, which it was possible, obviously. And then you could do a U sub. I could have figured that one out if I spent maybe another hour on it. But I wasn't really willing to. Question 20. Ooh, this one is a definite integral. Tangent over x to the 4th minus x squared plus 1 dx. I think I need another shot of shochu to really think about this one. I want to factor the denominator to start out. I think that might be doable. We'll see in a minute. But compi, cheers. Okay, is the bottom factorable? Well, I don't think there are any factors of 1 that add up to -1, so I'm going to say no on that. This is reminding me a lot of the derivative of inverse tangent, but we don't really have that going on in the denominator. Let's see, what if we factor an x squared out of the bottom? Could we do anything with that? Not obvious to me. I'm pretty stumped on this one already. The fact that it's a definite integral doesn't even change anything. Even if it was an indefinite integral, I just don't really know where to go with this one. Maybe this is another one where you have to complete the square, but I don't really remember how to do that. Let's just take a peek at the answer and see if I can sort of put myself in the right direction. Okay, the answer is 0. I don't really care about that because it's a definite integral. But how do you get to that? A to f of x over even f of x equals odd f of x. Minus a to positive a of an odd function equals 0. Okay. I guess that's all you need to know about this one. I never learned that about integrals, so I would never have figured it out that way. There's probably another way to figure it out, but I think I'm just getting too drunk to continue. If I can't figure out the next one, I think I'm going to end, because I think it might be... I think I might be reaching the limit at this point. Sine cubed times cosine squared. This one doesn't seem too bad on the surface. Yeah, we want the trig identities. Yeah, I don't know how much more I can do. My brain is getting pretty fried from the math and from the substances I've been drinking. So I think I need to subtract some intelligence for my performance over the last couple problems. Okay, my intelligence is at -3, whatever that means. Okay, so I'd like to get one of the cosines by itself so I can do a u-sub. I don't think I can do that using any trig identities, unfortunately. Or, no, actually, maybe the Pythagorean identity? No, that turns the whole cosine squared into 1 minus sine squared. I don't want that. Well, thank you for the congratulations, but I don't really know what I did. I guess just getting this far, but I didn't do 20 integrals. I got stuck on a good portion of them, so... Oh, just intelligence -3. Yeah. Yeah, achieving intelligence -3 is quite a feat, so I'll take the congratulations, never mind. Let's see, can I do anything with the signs? let's try that. That would become 1 minus cosine squared. Yeah, I think I've reached the limit. This one really doesn't seem that hard, but I just can't... I can't seem to find a way to the solution on this one. It's got to be some combination of trig identities, but I think I'm too many sheets to the wind to figure it out at this point. So let's check out the solution. So they used the Pythagorean identity to convert two of the sines to cosines, and then weave one of the sines, and then they did a u-sub. And then they went u equal cosine x, and then du equal minus sine x. Yeah, I should have been able to figure that one out, but I don't think I can do any more. That one was not that hard. What was the next one? Just curious. Oh, the next one looks pretty bad. Well, that's it for this fun little stream. Oh no, there's 100 of these. This whole document is 100 integrals. Actually, it's 101. I didn't know there was a bonus one. But, yeah. Yeah, there's a math YouTuber that I watch called Black Pen Red Pen, and he came up with this document of 101 integrals, and he made a video where he did all of them in one sitting and explained how to do them. It was a 6-hour video. So that's where I got this document from, and then I guess one of his viewers did like the answer sheet of it, which is really handy. Yeah. Yeah, I figured out some of them. I don't know, I'll give myself some credit because I feel like a lot of these integrals were made more for a YouTube video, and they're not something that you would encounter in like a textbook or something. I feel like they're made more for math enthusiasts than math students. So I don't know, it's still good, pretty good integral practice. If you can solve all of these integrals, you can definitely pass any calculus test that you'll come across. Yeah, these were pretty hard. But I think that's gonna be it for this stream. The other song that I had prepared for this stream was this one. I love that song so much. That's my favorite song from... That's my favorite hourly song from Animal Crossing New Horizons. I felt like it fit the vibe pretty well. Yeah, thank you. Thanks for tuning in, by the way. Well, this was kind of fun, and a bit embarrassing. You know, both getting a bit too drunk and showing my poor problem-solving skills on stream, but, you know, integrals are pretty fun. That's why there are a lot of, like, competitions between people to solve like really hard integrals, because they're just generally hard to do, and if you can figure out really hard ones, then that's a testament to your problem solving ability, which is just a generally useful skill for life, not just mathematics. Yeah, so I don't know if this will have helped me in preparing for actuary exams. I don't know if this will make me any better at integrals, but it was kind of fun to do. Thanks for tuning in. Thank you, Anthony Seha, for the kind words. And I'll perhaps see you next time. I've been working very hard over the past couple weeks on a new track that is at least halfway done at this point. I have a bunch of sections of the track basically built up. I just have to figure out how to connect them and make it flow as a nice complete track. That's pretty hard, but we'll get there. And it's a hardcore track, by the way. Yeah, so I'll see you later. Thank you guys for tuning in. Ta-ta for now.